Hello, people, and welcome back to another session. In this session, we'll be continuing our discussion from the previous session, where we learned about some of the basic terminologies with respect to the coefficients of simple linear regression. So, we learned about the residual coefficient, we talked about the regression coefficient, we also talked about how to calculate the sum of squares of these regression components for all the points and the residual component of sum of squares for all the points. We went ahead and we checked how to calculate the coefficient of determination or the value of r square. So up until now, this is the basic discussion that we had. Now we will move on and talk about statistical inferencing for our regression coefficients. So we'll be covering hypothesis testing in this session for our regression coefficients. Before we actually introduce the hypothesis test, let us first understand a few terminologies of the ANOVA table, which will be key in one way in conducting the hypothesis test in case of statistical inferencing about regression coefficients. So fundamentally, we will study two techniques to do our hypothesis testing for regression coefficients. The two ways are F test and T test. These are the two ways. These are the two ways in which we will conduct the hypothesis testing or statistical inferencing of our regression coefficients. Now, first we'll discuss F test, and in the next session we'll be discussing T test. So let me start the discussion for F test. Before I actually come to all the terminologies and all the knowledge that you need to go and perform the test, we'll have to look at a concept called the ANOVA table. Now, an ANOVA table consists of two components, in this case, the regression component and the residual component. So let us go over each of the terms associated with the ANOVA table. We have regression, we have residual, now we know how to calculate the regression sum of squares. So sum of squares value will be reg SS. Residual sum of squares is going to be res SS. We already know how to calculate that. Then the second column is for your degree of freedom for each of the components. Now the degree of freedom for our regression component is going to be K. Now K here basically represents the number of predictors, or we can say K represents the number of coefficients or the number of independent variables. Now it's very important to understand that in case of a simple linear regression, you only have one independent variable on which the dependent variable is dependent. But in case of a multilinear regression, you will have more than one independent variable. So in case of an MLR, you will have multiple independent variables and therefore you have multiple coefficients for those independent variables. But in case of a simple linear regression, there is only one. So the number of predictors for your simple linear regression or K is going to be 1. And the residual degree of freedom is going to be N minus K minus 1. N is the number of observations in the sample. K is the number of predictors. And so you do n minus k minus 1 to get the value. So for simple linear regression, this is nothing but 1 and n minus 2, only for simple linear regression. Then you calculate the regression mean squared and residual mean squared. Regression mean squared is regression sum of squares divided by the regression degree of freedom, and residual mean square is residual sum of squares divided by residual degree of freedom. And finally, to conduct the F test, you need to calculate your test statistic. So your test statistic for an F test will be regression mean square divided by residual mean square. Okay, and for each of these two values, you can substitute the value from here. This is my value of test statistic. Now we will come to the actual process of hypothesis testing, setting up the null and alternative hypotheses, and calculating the critical F value, and how to calculate the critical F value. Let me just quickly remove this. Okay. So my null hypothesis here is going to be, so basically what we need to show, or what we need to find evidence for, is there is a linear association between my independent and my dependent variable. Okay. So what we need to find that, suppose I have my x and y axis and have some points. So I need to find evidence that there is a linear association between my x and y. And so I'll start with assuming that there is no association. So rather than a straight line, y has no association with x. Okay. So my assumption or my null hypothesis is that there is no linear association between x and y. And if there is no linear association between x and y, the slope or the coefficient of my independent variable in the equation of linear regression is going to be 0, which means beta 1 will be equal to 0. This is my null hypothesis assumption. So I'm starting from here, and I have to find evidence for that there is actually a linear association between my x and y variable, and that linear association can be positive or it can be negative. Okay. So my alternate hypothesis will be beta 1 not equal to 0. So understand once again, in my null hypothesis, I'm assuming that there is no linear association between x and y. And when there is no linear association, the graph is going to look something like this, where there will be a straight line parallel to the x-axis, which means the slope of the line is 0. Therefore, my null hypothesis is beta 1 is equal to 0. And my alternative hypothesis is I need to find evidence that there is linear association regardless whether it is positive or it is negative. Therefore, my alternate hypothesis is beta 1 is not equal to 0. Now, if we are doing this example, or if we are basically finding our alternate hypothesis or evidence for alternative hypothesis using our F test, then the F test is done at, or the F test is conducted at one and n minus 2 degree of freedom. Okay. And there is a property for F test. Now, this is where our discussion gets extremely nuanced, because from our previous sessions, you might, your first thought will be that because I need to find evidence for my slope is not equal to 0, which means my slope can be either positive or it can be negative, this has to be a two-sided test. Your assumption is correct if the test that we would have taken was a t-test. If our test would have been a t-test, then your assumption is 100% correct. However, the property of f-test is it is always one-sided. This is a specific property of f-test. F-test is always one-sided. And therefore, rather than doing the test at alpha by 2 level, at the alpha by 2 level, we'll be doing it at alpha level. So the property of f-test is this right here. This is always one-sided, and this is my f critical. This is my confidence level. Okay. So now how do we do this using R? Now in R, you saw the functions we have for Z test and for T test, right? So you saw P norm, Q norm. This is for Z test, PT, QT. This is for T test. Now for F test, we have PF and we have QF. So these are the functions that you will be using when you will be performing F test to surmise statistical inferencing about regression coefficients. I'll stop right here for this session. We'll see an example in R when we meet the next time. The important point to take away from this session is knowing how to calculate your F statistic value, which is the regression mean square upon residual mean square, and knowing that your F test is done at 1 and n minus 2 degree of freedom, and F test is always one-sided. These are a couple of key points that you should remember. In the next session, when we'll see each other, we'll be going over an example in R. Thank you so much for watching. I'll see all of you all in the next session.